video, we're going to talk about dense subsets and separable spaces. So here are our definitions. A subset A of a topological space X tau is dense if A closure is equal to X. So that's A closure if the closure of A is equal to the entire set. And a topological space X tau is separable if it has a countable dense subset. So let's just think about our previous definitions in relation to these. So X is in the limit points of A, and we know that A closure is A unioned with its limit points. X is a limit point of A if for any open set U containing X, there is some Y other than X such that Y is in that open set as well as A. So here we have a slightly different picture than usual with our set X and our points A. So A are these purple points sprinkled throughout X, and let's have X just be some random point of X. Then it's a limit point of A if for any open set U containing A, there's some point of A other than X itself that's in that open set U. And of course, since A closure is equal to A together with its limit points, that means that we kind of don't need to worry about this extra condition of Y not being equal to X, because if Y was X, then X would in fact be in A. So X is in A closure if and only if, for any open set U containing X, the intersection of U and A is not equal to the empty set, or there's something in A that is in that set U. So that means that A is dense in X if A closure equals X. That means every non-empty open subset of X contains a point of A. Why is that the case? Again, if we think about just some arbitrary point, say Y in X, every open set containing Y must contain some points of A. That would be, fulfilling this requirement. And since we're looking for A closure to be equal to X, it's got to be true for every point Y that's an element of X. Okay, so let's look at a couple examples. Let's let A be the set of odd integers, the set 2k plus 1, such that k is an element of the integers. Let's think about a couple different topologies on the real numbers and think about whether A is dense in each of these. So if tau is the usual topology on R, so that is the one induced by the metric distance between x and y is equal to the absolute value of x minus y, then is A dense in this normal topology or usual topology on R? Secondly, if tau sub c is the finite complement topology on R, then is A dense in this topology on R? Next is R, the real numbers with the finite complement topology, a separable space? Does it have a countable dense subset? Next is the real numbers with the usual topology on R separable? Does it have a countable dense subset? And finally, is the real numbers with tau sub d, where tau sub d is the discrete topology, is that a separable topological space? So pause on these, try them out, and then we'll talk about them together. All right, so if we've got our odd integers and tau is the usual topology on R, so is A dense in this topological space? So in this topological space, some open sets are open intervals, so we can also think of it as epsilon balls. X sub e is the open interval x minus epsilon to x plus epsilon, are open balls and therefore also open sets in R with the usual topology. Unions of those things are also open sets, of course. But can we think of, some x in the real numbers, let's say x equals 1.5 and epsilon equals 0.2, then the ball centered at x of radius 1.5, or in other words, the open interval from 1.3 to 1.7, contains no integers, right? Contains no elements of A, and therefore A is not dense in R, tau, because A closure is not equal to the entire set of real numbers. If A closure was equal to the entire set of real numbers, then any open set in R would contain some integer. Or more specifically, there are open sets that do not contain odd integers. So now let's look at our next example. A is still a set of odd integers. Now we're looking at R with the finite complement topology. So is A dense in this topological space? In other words, is A closure equal to all of R? So let's let X be an element of the real numbers, and is X an element of A closure, of the closure of the set of odd integers? So to determine this, we can let U be an open set containing containing X. So use an open set containing X in the finite complement topology. So in tau sub C, and it contains X, so it's non-empty. So U complement is finite. That's by definition of the finite complement topology. Since U complement is finite, this tells us that A cannot be a subset of U complement. A is all odd integers. That's an infinite set, can't be a subset of U complement. So therefore, U intersect A is not the empty set. So X must either be a limit point of A or X must be an element of A. In other words, X is an element of A closure for all X in the real numbers. And so A, the set of odd integers, is dense in R. So now let's look at these questions of separability. So first of all, is the real numbers with the finite complement topology a separable topological space? We just showed above that it is. Yes, because A, the set of odd integers, is countable. It's countably infinite. And A is dense in this topological space in R with the finite complement topology. So that means that this topological space is separable. Next, is R with the usual topology separable? Well, we saw above that A is not dense in R with the usual topology. The odd integers are not dense in R with the usual topology. So this is a countable set that is not dense in this topological space. But that doesn't answer the question. The question is there some countable set which is dense in this topological space? The answer here is actually still going to be yes. So what countable set meets that criteria? So we've seen before that the rational numbers, rationals, Q, the rationals, are dense in the real numbers. So just to remind ourselves why that's true, which we've talked about before, if we take any open set, x minus epsilon, x plus epsilon, then there exists some y in the rationals such that x is in between these two values, such that y is in this x minus epsilon, x plus epsilon. We actually proved this way before we even introduced a metric space, that between any two real numbers is a rational number. And so any open set will contain, in R with the usual topology, any open set will contain some epsilon ball, and therefore any open set contains this. And so, yes, any open set in R with the usual topology contains some element of Q, and Q is countable. So Q, we also proved this, is a countable set. It's countably infinite. So R with the usual topology is a separable space because it has a countable dense subset. Lastly, we're looking at, or in this example, we're looking at R with the discrete topology. So recall that the discrete topology, that means every set or every subset of R is open. The discrete topology is a topology on any set, on any non-empty set, and it's the topology in which every subset is an open set, or every subset is an element of tau sub d. So could R be separable? Is there some countable dense subset? Then our answer is no. So for any countable subset, let's say B of the real numbers, B cannot be dense, the closure of B cannot be the whole set of real numbers. So we know that the set of real numbers is uncountably infinite, and if we're looking at a countable subset, then B is a subset of R, but not equal. So there is some X that's an element of R, which is not an element of B. Then, because every subset of R is open, that means that the singleton set X is open in the real numbers with the discrete topology. And so X is an open set, and B intersected with X is non-empty. Or sorry, is empty. B intersected with X is empty. So therefore, for any countable subset B of R, the closure of B is not equal to all real numbers. And so that means that R with the discrete topology is not separable. Our last definition in this section is of a subset being nowhere dense. So a subset B of a topological space X tau is nowhere dense in that space if the interior of B closure is equal to the empty set, if the interior of the closure of B is equal to the empty set. So let's again look at the set of odd integers as a subset of the real numbers in two different topologies. So first, A is nowhere dense in the real numbers with the usual topology. Let's show that that is the case. What is a closure in R with the usual topology? We didn't exactly fully answer this, but a closure in this topology is going to just be A, the set of odd integers, because if X is an element of R and not an odd integer, then we could let, say, epsilon be the minimum distance between X and any odd integer. And then that would tell us that the ball centered at X of radius epsilon is open, and this ball centered at X of radius epsilon intersected with A is equal to the empty set. So if X is not an element of A, then X is not a limit point of A, and therefore A closure, which is A together with its limit points, A closure is just the set A. So that means that the interior of A closure is just the interior of A. Now let's think about this set. We know that the interior of A is a subset of A. So let's let Y be an element of A. Is it in its interior? Is there any open set containing Y that's completely a subset of R in the usual topology? No. Any open set containing Y in R with the usual topology also contains the set Y minus epsilon, Y plus epsilon for some epsilon sub greater than 0. And so this is not contained in A. Clearly, A, the set of odd integers, does not contain any open intervals. And so y minus epsilon, y plus epsilon is not contained in A. So therefore, the interior of A closure, which is the interior of A, is the empty set. And so A is nowhere dense in R with the usual topology. Now what about in the finite complement topology? So in the finite complement topology, we saw that A closure is the entire set of real numbers. So in the finite complement topology, A is dense in R with the finite complement topology. And therefore, we've already seen this example all the way through. The closure of A in R with the finite complement topology is the real numbers, the whole set of real numbers. So it can be the case that the same subset of the same set with different topologies can have very different properties. In R with the usual topology, the set of odd integers is nowhere dense. In R with the finite complement topology, the set of odd integers is dense.